Okay, so we pick up from question 10. So graphene, this is graphene, the new molecular material made from carbon atoms. So this is like graphite, but it's just one layer thick. So graphene is one layer thick of graphite. So we can see the structure here, suggests why graphene is an excellent conductor of electricity. We all got that. Oh, you all got that. It's got free electrons that can move. So the answer being it's got electrons that can move and carry charge. Okay. The second one is explain in terms of structure and bonding why graphene has a high melting point. Well, it's got a high melting point because these are covalent bonds, and these covalent bonds take an awful lot of energy to break. So if it takes a lot of energy, then the melting point is going to be high. So for this particular part, we'd say covalent bonds, which are very hard to break and or need a lot of energy to break on this particular one. Okay. Here, there are several types of crystal structure and bonding shown by elements and compounds. Sodium reacts with chlorine to form sodium chloride. So sodium chloride, we're on a bonding paper, so that must be because, so that would be ionic. Why is the melting point of sodium high? So here I need you to say that it's ionic and then give me the definition of ionic bonding. So we'd say it's ionic, and then we would say we've got strong electrostatic forces of attraction between oppositely charged ions. Okay, we could say between oppositely charged, a sodium plus ion and a chloride minus ion, but this is just a definition of an ionic bond. B, the table below shows the melting points of some sodium halides. Okay, so you can see the melting points, we can see the melting points going down. Why do the melting points of sodium iodide, why is it lower than sodium bromide? So if we were to draw that, we've got sodium and iodine is in the next period down to bromine. So bromine is one side. That's Na plus, Br minus. The sodium atom in sodium chloride, sodium iodide. The sodium ion is the same, but the iodide ion is bigger. So we've got small ions as opposed to big ions. So it's the size of the ion here that's making the difference. So we could say that you can't say iodine because iodine's an atom, so we have to say iodide or bromide. So the iodide ion is bigger than the bromide. Okay, and that's it. But we can't say iodine or bromine. It's the wrong terminology. Question 12. So we can see that fluorine forms many compounds with covalent bonds. State the term, what the term covalent bond is. So this is, again, it's a definition, and it's a shared pair of electrons. So we need to the shared pair of electrons. So that's got to come in there between atoms. Okay, so it's a shared pair of electrons that's between atoms. Between atoms. You could say a covalent bond, two atoms donate one electron each to share a pair of electrons. It comes down to the same thing. Write an equation to show the formation of one molecule of ClF3 from chlorine and fluorine molecules. So again, I would expect you to know the formula of chlorine, which is Cl2, and fluorine, which is F2. And that's going to form one molecule of ClF3, or 1 mole of ClF3. So if I'm only going to have one of these, then my equation on this side has got to have or produce one chlorine. So to do that, I would put a half in front of here. So a half times 2 chlorine atoms would give me 1 chlorine atom. So a half times 2 is 1. And I need 3 fluorine molecules. So if I put a 3 in front of that, 3 times 2 is 6, which is 3 too many. So it'd be 3 over 2 fluorine. Okay, so a half chlorine and 3 over 2 fluorine would give me 1 ClF3. Okay, now I need to know the shape of CCl2F2. So draw the shape of the dichloro-difluoromethane molecule and the shape of the chlorine trifluoride molecule. So again, in this, we're going to have to do 2 shapes. We always do 2 shapes. If you're only drawing 1 shape, you really do need to look and check. So we know our central atom is carbon. We've got 1, 2, 3 electrons because carbon is in group 4. We've got 2 chlorines that will create a covalent bond. So 1 chlorine, 2 chlorine. So they bring in their electron to bond. So we've got 2 chlorines, and then we've got 2 fluorines. So the fluorine will bring its electron to bond. Okay, so what we've got here, we've got 4 bonding pairs, and the shape of that would be tetrahedral. So draw the shape, include any lone pairs that influence the shape. It's not asked us to name the shape, but I think out of good practice, I would name it anyway. It's tetrahedral, and I'm going to put the bond angle of 109.5. It doesn't ask for it, but I think just as a matter of course, it's a good idea to put it, because then you will get into that habit and you won't miss any extra marks when they ask you to name the shape. Okay, so ClF3. So Cl is the central atom. Chlorine is in group 7. So 1, 2, 3, 4, 5, 6, 7. And then I've got 3 fluorines bonding. So 1, 2, 3. And then I'm going to pair up these. So I've got 3 bond pair and 2 lone pair. Okay, so that's got to be based on trigonal bipyramid. So a trigonal bipyramid. Okay, now they did say draw the shape. So whilst I've actually only sketched a shape out there, I need to draw it. So I need to put in the wedges. Whoops, that's going to come, that's the C in the center. There's the wedge coming out. That'll be F, that'll be F, that can be C, L, and that can be CL. So there's my shape. With this one, it's a trigonal bipyramid. So I'm going to have that down the center, that coming out here, a dot that way, and a wedge that way. So the chlorine will be in the center. I've got these 2 to put in. Now they can go opposite to each other, or they can go equatorial. And I think in our lesson, we decided equatorial was far better. So this is what we've got. So this is based on a trigonal bipyramid, which now shows me that it's T-shaped. Okay, so it's based on trigonal bipyramid, but this is T-shaped. This is based on a tetrahedral, and it is tetrahedral. Okay, we can work out the bond angles here. So these should be round about 90, but with the push of those electrons, this is probably a little bit less, maybe 85-ish. But it's not asking for them, so I'm not going to give that information. Okay. So we're on the back of this now. So BF3 is a covalent molecule, and it reacts with F- to form BF4-. So name the type of bond. So let's draw it out. So boron is in group 3. 1, 2, 3. It's got a minus, so I'm going to add an extra electron because that's the extra electron to give it a minus sign. And it's bonding with 4 fluorines. So let me start again. Boron, trifluoride. Boron is in group 3. So we will only have 3 fluorine atoms bonding to boron. And that means we've got a vacant area here for F minus ion to donate to. So if we were to put the electron pairs around fluorine, fluorine would have 4 electron pairs around it. So it's going to donate a pair of electrons to boron. So what type of bonding is that? That's dative or coordinate bonding. And the explanation behind that is the lone pair of electrons both come from fluorine. So both electrons come from fluorine. Okay, so it's a dative bond that both pairs of electrons come from fluorine and they're donated to the BF3. So both electrons come from fluorine and are donated to the BF3 molecule. Okay, state the bond angle in BF4 minus. We've got 4 electron areas of the electron density around boron, so the angle is 109.5 degrees, which is the tetrahedral angle. Okay, and this final question is based on diamond and graphite structure. So being able to explain why the property is as it is. So in diamond, you're able to scratch diamond. It does say that it's very that they have high melting points. Okay, so we've got to describe this in terms of its structure and its bonding. So in diamond, we can say that it's macromolecular or giant covalent, macromolecular or giant covalent. It's got 4 covalent bonds per carbon. Okay, so with those covalent bonds, they are in a tetrahedral shape. So those covalent bonds make diamond hard, so the crystal is strong. So diamond is hard. Okay, the other thing we can say here is covalent bonds need to be broken. Okay, so the melting point is high, as a lot of energy is needed. A lot of energy is needed. Okay. Graphite may be used as a lubricant. So what we can say here that let's see, graphite's arranged in layers, so it's in layers which can easily slide, so they easily slide over each other because we've got weak van der Waals forces, which are easily broken. Okay, diamond and graphite both have high melting points. Actually, I put that up there, but it needs to come down here. So they have high melting points because they're macromolecular. They've got strong covalent bonds. Which require a lot of energy to break. Okay, and that means so strong covalent bonds require a lot of energy to break. So that means they've got a high melting point. So it gives rise to a high melting point. Let me see. One of the other differences is that diamond is a non-conductor. Or you could have said graphite conducts electricity. Okay, so they're the same thing, it's just worded differently. I suppose one of the other differences is their appearance. Diamond is a bright crystal and graphite is a black solid. Oops, okay. So diamond's a non-conductor or graphite conducts electricity, one or the other. Or diamond is a clear crystal used in jewellery, whereas graphite is a black solid. Okay, and I think that's us done.